Math 1325, time for review for test 2. So in MyMathLab, the review for test 2. And then on Thursday of this week, you'll see test 2 appear right here between the review and section 5.1. And that'll have a 48-hour window. You can take it one time, anytime on Thursday or Friday. Thursday or Friday, and then Friday night, October 21st, that's when all 7 of these homeworks are due, plus the review and the test. So we had 2 sections of Chapter 3, rates of change and definition of derivative, and then we had all the derivative rules basically after that. So review for test 2. Find the average rate of change. That's one of the few things here that's from algebra and there's no calculus behind it. So average rate of change is different than just saying rate of change or instantaneous rate of change. Average rate of change on a function like f of x equals x squared plus 10x, that's a quadratic. So if you have a quadratic graph that's curved in a U-shaped pattern, if you go from one x value to another, the average rate of change is actually the slope of a secant line that only passes through that curve twice. So average rate of change is just the slope of a secant line. If you do instantaneous rate of change, or just later on in chapter 4 they just say rate of change, which implies instantaneous. Instantaneous rate of change is the slope of a tangent line where you just touch it once. And that is a derivative. Derivative is slope of a tangent line. So derivative is not the average rate of change. So I'm given a function, f of x equals x squared plus 10x. They want me to go between x equals 0 and x equals 7. So this is literally no different than slope in algebra. Average rate of change. In algebra, we say y2 minus y1 over x2 minus x1. Here they'll say f of x2, or f of b sometimes, but we've got an x1 and an x2 right here, minus f of x1 over x2 minus x1. Or maybe f of b minus f of a over b minus a if you call this one a and this one b. They sometimes do it that way too. But it's really just the slope formula. So I can find f of 7. What does y equal when x is 7 is what that's saying. F of 7 is 7 squared plus 10 times 7. That's 49 plus 70, 119. F of 0 is 0 squared plus 10 times 0, which is 0 plus 0, that's 0. So the average rate of change would be 119 for f of x2 minus 0 for f of x1 over 7 minus 0. And if they would have given me any x besides 0 for the first one, then these would have probably been non-zero. But it makes it a little easier when they are, because then it's just 119 over 7. I didn't really have to subtract anything. 119 divided by 7. First thing I do is check if it comes out exactly. It did, 17. If it doesn't come out exactly, then we would leave it as a fraction and try to reduce it if we could. So the slope of the secant line between 0, 0 and 7, 119. See, this would be, the graph I drew was just a generic one, but this would be some kind of graph that would be going like so, and 0, 0's here. 7 and 119 is so high up it's off the screen almost, so the secant line would be well off the curve for most of the time. That would be the secant line slope. And that would have a slope of 17, so you'd be going up 17 over 1, up 17 over 1, over and over again. So the average rate of change, or the slope, is 17 for that secant line. So again, on these reviews, they count as a major homework grade. In essence, getting 100 on this one review is equivalent to getting 100 on all 7 of the other homeworks. So they're each worth all the review, the average of your reviews and the average of your homework are equally weighted, in other words. And it's like the MyMathLab thinks you're doing a test, though. This is like a practice test. So I don't have all the ways to check my answer or help me solve this. All the help isn't here. So you just put your answer in like it's a test, go to the next one, and then when you're done, submit it. And once you get a grade you're happy with, then you don't have to do it again. If you want to do it more than once, you can, and only the highest grade counts. And if you get a grade you're happy with, then you don't have to do all of the problems on a future attempt. But if you want to beat your current high score, then unfortunately you have to do everything all over again. Suppose that the position of an object moving in a straight line is given by this s of t. That's what they do in physics for position functions, is s of t. And then they move to velocity, which is v of t, and then acceleration, a of t. So the position function is quadratic, 3t squared plus 5t plus 5. Find the instantaneous velocity, which is the same thing as instantaneous rate of change, or derivative is really what that is, when t equals 6. Now, they meant to have you, and I'll do this in a future problem, but one advantage at this point is you know how to find derivatives now, or at the time, with shortcuts, where at the time you didn't. So this could save time on both the review and the test. 5t plus 5, okay. The derivative of this, s prime of t, which actually is velocity. Derivative of position is velocity in physics. You could use the power rule here. 3 times 2 is 6. T to the first power plus 5, since that's linear. And the derivative of 5 is nothing. What was intended to be done was to do limit as h approaches 0 of s of t, usually it's x, but we use t here, t plus h minus s of t all over h. This is the definition of a derivative. So we can do that, but it takes like 10 minutes per problem that you get to do one of those. Instead, you can do it in 10 seconds with the shortcuts of derivatives. So find the instantaneous velocity when t is 6, and now I can just plug 6 in into the velocity, or the derivative of position. 6 times 6 plus 5. 36 plus 5 is 41. So after 6 seconds has elapsed, the object is moving at a speed of 41 miles per hour, or whatever the units happen to be. I don't know if they didn't give us any units here, but whatever that is, 41 meters per second, 41 miles per hour, or whatever it is, that's how fast it's moving at any given time. So same thing here. No, this is different, I'm sorry. So here it says find the average rate of change. That's not a derivative. This is back to the same as problem number 1. We're just doing a business problem. So we have profit in hundreds of dollars from selling X items is given by P of X equals 5X squared minus 7X plus 10. Complete parts A through D. We want average rate of change from 2 to 4 first. So our profit function, P of X, is a quadratic function. 5x squared minus 7x plus 10. And we're going from 2 to 4 for part A. Average rate of change. That's slope of a secant line. So this is where I'm going to do f of 4 minus f of 2 over 4 minus 2, just like the slope formula of algebra. So we just need to calculate f of 4 and f of 2 first. Here's where another way you could speed things up. Get mine to come out. Okay. So I can quickly do both of those right here. If I type 5 parenthesis, I'll do the 4 first. 4 close parenthesis squared minus 7 parenthesis 4 plus 10. So I've plugged in 5 parenthesis 4 parenthesis squared minus 7 parenthesis 4 parenthesis plus 10. And that's 62 right there, if you can see that. That is f of 4 right here. Or you can do it slower with a simpler calculator too. 62. And then I can repeat this for f of 2. And you could probably do this maybe faster in your head than by typing in a calculator, but 2 squared is 4. 4 times 5 is 20. 7 times 2 is 14. 20 minus 14 is 6. 6 plus 10 is 16. So that here, if I press second enter, it calls up the last statement I put in there. And then I can back up on top of those 4s and type 2s. And 16 that way too. And then 4 minus 2 for the denominator. So the numerator is 46. The denominator is 2. So 23 is the average rate of change. And again, these are like coordinates. When x is 2, y is 16. When x is 4, y is 62. And you have a curved graph. A curved graph that's going through the coordinates 216 and 462. And that's why it's a secant line, because we're doing average rate of change. That slope of that secant line is 23. Well, the difference between 2 and 4, that's a distance of 2. Then it shrinks down to a distance of 1 next. Okay, so wait a minute. I got 23 for this answer, but this is the tricky part. It's in hundreds of dollars. So that's actually 2,300, not just 23 when you plug the answer in. So they often do this where the units are in the problem, and then you got to adjust your final answer to that. 2,300 per item, not 23 per item. So average rate of change, you can go from 2 to 4, you can go from 2 to 3, you can go from, okay, I guess I thought maybe they're going to do another one later, but that's what going from the slope of a secant line to the slope of a tangent line is all about, is you start shrinking this distance down until it approaches 0. When the distance between these two values gets closer and closer to 0, that's the definition of a derivative. That's what this limit as h approaches 0 means. I'm shrinking that 2 to 4 down to 2 to 3, and then maybe 2 to 2.1, and so on. Closer and closer and closer to 0. Then you switch from slope of a secant line to slope of a tangent line. The 4 maybe shrinks down to 3, so now the secant line is less steep. Then you could shrink it down to 2.1. All the way as close as possible to there. When it gets close enough, then you're just touching it once. So part B is f of 4 minus f of 3 over 4 minus 3, or it was at 3 and 2. Oh, sorry, it was 3 and 2, sorry. F of 3, I knew they were one away from each other, but f of 3 minus f of 2 over 3 minus 2. And we already know f of 2 is 16. We have 3 minus 2 here. The one new thing here is f of 3. We don't have that, but here's where the graphing calculator helps. Second enter and change all the 2's to 3's. 34. I can quickly get an answer for that. 34 minus 16 is 18. 18 divided by 2, or divided by 1 is 18. See how it's a little less steep? It went from 23 to 18. This is a slope of 23. It's steeper. This is less steep. That's a slope of 18. Although we're really talking 1800, not 18. Find and interpret the instantaneous rate of change of profit with respect to the number of items produced when x equals 2. This number is called the marginal profit. Remember, marginal, anything is derivative. Instantaneous rate of change is derivative. Okay, so normally if you were doing this section back when we learned it, you would have to use that definition of a derivative. Now we can speed things up and just do the power rule for part C. P prime of x is 10x minus 7 for that linear part. That's the derivative in general. And then they're saying when x equals 2 exactly, P prime of 2, 10 times 2 is 20. 20 minus 7 is 13. See how this is getting less and less and less till you hit the instantaneous rate of change. So your secant line went 23, then it went, 18. When you actually have a tangent point here, then it's got a slope of 13 is what that's saying. Oops. So then it's 1300 per item. And remember how the other interpretation of this is going to the next item, but I don't see that here. Okay, so I guess they're not doing that. But when 2 items are sold, the profit is increasing. When items are sold for so much, okay, the 2 is not, what is the x again? It's best to come up here and see the x. Suppose a total profit in hundreds of dollars. X is the profit. So the profit was 1800, not 2. So the 2, the x are the number of items. So it's definitely when 2 items are sold. When 2 items are sold, it's not when items are sold for $2 or a rate of $2. When 2 items are sold, the profit is increasing at a rate of 1300 per item. That's the interpretation. It's definitely not decreasing, and it's not those other two because they're backwards. So find marginal profit at x equals 4. That's using your derivative and just doing P prime of 4. P prime of 4 would be 40 minus 7, 33. So now if you could sell 4 items instead of 2, maybe you're selling like tractor trailers that are very expensive. You don't sell very many of those in a given period either. So now I doubled my sales from 2 to 4, and now the rate of change is increasing much faster, 3,300 instead of 1,300. Okay, that's the end of that problem. See, use the definition of the derivative, find f prime of x, then find f prime of 1, 2, and 3. And you could easily use the power rule, but let me just do the definition of a derivative one time out the long way, just to review that. And on the test, of course, it doesn't require any work to fill it in, so they're not going to know which way you did it. F of x is negative x squared plus 9x minus 8. So if I do limit as h approaches 0, oops, I'm trouble writing that. Okay, f of x plus h. So you go a little bit past x, and then you minus the original f of x and divide by h. And h will get close to 0, so I can't plug 0 in for h. I need to get rid of that denominator h somehow. Limit as h approaches 0. So I'll do a bracket for this f of x plus h. So I need to replace this x with x plus h. There'll be a negative x plus h squared plus 9, then replace this with x plus h minus 8. That whole bracket is the f of x plus h. Minus, then I do another bracket for f of x where you just rewrite that all as is. All over h. This again, we did this a number of times back in chapter 3. When you square a binomial, you get x squared. You square the front part. You multiply these together and double it, so then you get 2xh or 2hx, however you want to write that. And then you square the h and get h squared. And then this negative applies to all three of those. So negative x squared minus 2xh minus h squared plus 9x plus 9h minus 8. 6 different terms right there. There's 3 terms here. So we distribute the negative, and that switches them all. The negative x squared switches to positive x squared and cancels with a negative x squared over here. The positive 9x switches to negative 9x and should cancel with positive 9x. The negative 8 switches to positive 8 and cancels with a negative 8. Everything in the second bracket always cancels out. If it doesn't, you did something wrong. And all remaining terms have h's in them, so then I can factor that out as a GCF. Like that. So negative 2xh, take the h away, you're left with negative 2x. Negative h squared, you're taking one h away, but there's still one more, negative h. And then 9h, take the h away, you just have 9. Boom, boom, those cancel finally. Now I can finally plug 0 in because it won't make the bottom of the fraction 0. Undefined. So that h, this minus h here will go to 0, and just anything plus or minus 0 won't matter anymore. So the derivative by using the definition is negative 2x plus 9. This is f prime of x in general. It's a whole lot easier to do the power rule. 2 times negative 1 is negative 2. Decrease the exponent by 1. Plus 9x, the derivative of that's just plus 9, and the derivative of negative 8 is 0. So obviously the derivative was negative 2x plus 9. So I just went through this one more time to show you why that's true again. But on the test, nobody's going to know which method you use. So negative 2x plus 9. Now it's very easy to do f prime of 1, f prime of 2, f prime of 3. Put 1, 2, and 3 in right here. Plug 1 in, you'll get negative 2 plus 9, which is negative 7. I'm sorry, 7, positive 7. Then plug 2 in. 2 times negative 2 is negative 4, plus 9 is 5. And plug 3 in. Negative 2 times 3 is negative 6, plus 9 is 3. So the slopes are getting less steep as you're going there. The slopes of those tangent lines would be less and less steep. Okay, so that was 4. Again, you can use the definition if you want, but here's an easier way on number 5. If the original function is 2 over x, or 12 over x, you could rewrite that as 12x to the negative 1 as a power. We didn't do this in chapter 3 when we were doing the definition of a derivative. We would do f of x plus h minus f of x all over h. And then the idea is you get common denominators. If you remember that when we did that back then, But here I can just go f prime of x equals power rule. -1 times 12 is -12. Base stays the same, and then you decrease the exponent by 1 to -2. And technically the chain rule is happening too. You're doing the derivative of the base, but x is just linear, so the derivative of that is 1 on its own. So there's technically a times 1 for the chain rule here. And then I could rewrite it as -12 over x squared and put it back the way it looked originally, which doesn't matter. But if I'm going to be plugging numbers in, maybe I want that because it'll make it easier to do f prime of numbers into this than into this one. F prime of -2, 0, and 6. If I put -2 right here, you'll get -2 squared is 4. -12 divided by 4 is -3. So we want this answer and all these answers. Plug 0 in. 0 squared 0. 12 divided by 0 is undefined. So the derivative at 0 is undefined. So that means you can't draw a tangent line there. It's because the original function doesn't even exist at 0. There's a vertical asymptote at 12. A graph 12 over x looks like this. And it's got a vertical asymptote at 0, so you can't do f prime of 0. You can't do a derivative at a spot where the original graph doesn't even exist. So any place that's discontinuous is a potential issue. If you have asymptotes, holes in the graph, anything that's undefined like square roots that are negative. And then also you can't do spots where there's a vertical tangent line because then vertical slope is undefined. And you can't do corner points either. Not that this involves that, but those are just a review of that. So 6 squared is 36, -12 over 36. Both of those divide by 6, so -2, 6. Actually, they both divide by 12, so -1/3. If you're ever reducing a fraction and you don't do it by the largest amount possible, it's okay if you recognize that it goes again. I could have divided both of these by 12 and got right to the answer first, but I saw 6 right away and didn't think the largest one instantly, but I still got to the answer eventually. So the derivative in general is -12 over x squared, which you would get that same answer even if you did the longhand definition of a derivative with limit as h approaches 0. And then when I plugged in -2, can't even get to that. There it is. -2, that one was -3. When I tried to plug 0 in, it was no bueno because there's no derivative there if the graph doesn't exist there. And then 6 gave me -1/3. Okay, number 6. Find the x value or values where the graph does not have a derivative. So I just listed those things. You'd want to see, is there any asymptotes? Is there any breaks in the graph, like a piecewise function? Is there any undefined spots? Is there corner points? We have one of those. Is there vertical tangent lines anywhere? No. So apparently this corner point's the only issue here. And that's exactly at an x of -2. You can't draw a tangent line to a corner point is a problem because if you're a little to the left of it, it's kind of sloping steeply down, but a little bit to the right, it's going in a positive slope. Normally, if you're a little to the left, a little to the right, they both are very close to each other. So that was all there on that problem, was just the things that make us not have derivative answers. Okay, I think this is the final problem from chapter 3, and then all the rest is chapter 4. So we have the demand function. D of P is another quadratic. P is the price of the item in dollars, in just regular dollars, not hundreds of dollars. Find the rate of change, not average rate of change, but rate of change of demand with respect to price. That's another way to say derivative. And then find and interpret it when the price is 8. So this took a long time to do back in chapter 3. Now it can go much quicker. If d of p equals negative 3p squared minus 7p plus 200, part A wants the rate of change, not average rate of change. That's derivative d prime of p. Or it said find the average rate of change of demand with respect to price. So that's the second variable, the price. Remember those dy over dx's, so you can sometimes write d over dp is another way to write this. Okay, so I can just use the power real quickly and get negative 6p to the first minus 7. Or do the definition version the long way. This is the derivative in general. That's what part A wants. So negative 6p minus 7. Now plug 8 into that. So find and interpret the rate of change of demand when the price is $8. Put an 8 here. Negative 48 minus 7 is negative 55. So when the price is $8, demand is decreasing, because it's negative, at a rate of about 55 items for each increase in price of $1. So see, the confusing part is it was about $8. We plugged $8 in. Price is $8. P is price. Demand is, P represents the price in dollars. Demand, it doesn't really say what the units for that are, so it makes it a little harder to interpret it, but okay, so the derivative is negative 55 when the price is $8. So it should be this one here about the $8, not... So yeah, items. See, there's no units because there's items. So you're selling your items, you have a store, and when price goes up, demand goes down. That's the law of supply and demand. So if the price is $8, inflation's hitting, maybe you're selling pencils and they used to cost $1, now all of a sudden they cost $8. Well, nobody wants to buy an $8 pencil anymore. So the rate is decreasing and could be decreasing fast. People don't want the item if you overprice it. So price of $8, they're going down 55 items for each increase in price. And the price is 8. Now I still think it's this one actually, because the $8 is right here already. When the price is $8, demand is increasing, because remember, rate of change. What I really got, when you get this rate of change, d prime of p, remember how average rate of change is slope? Well, instantaneous rate of change is a slope as well. It's just a slope of a tangent line instead of a secant line. So when you're plugging in $8 for p, and that's how you're getting negative 55, this is really the slope of a tangent line. And slope can be written over 1 if it's not a fraction already. So each time the x-coordinate increases by 1, the y-coordinate is decreasing by 55. That's what slope is, rise over run. So I'm going down 55 and over 1, and it's happening when price equals $8, but I could change the price to something else. And because the derivative was an integer, then it's compared to 1 in essence. If you somehow got a fraction like negative 55 over 2, just because it didn't reduce, then it would be compared to $2 instead of $1. But that's why it is C. When the price is $8, demand is decreasing at a rate of about 55 items for each increase in price of $1. That's what derivatives are telling you. At that moment in time when you increase by $1, say from $7 to $8, then you watch and see what happens to your demand of your item. And if it's decreasing, that's bad for you because then you're not going to make as much profits. If I did a different dollar price, like let's say I dropped my price to $7, I'm noticing people aren't buying it, so let's lower the price. And now this is negative 42 minus 7, which is negative 49, but that would be over 1 as well. So if the price was $7, demand would be decreasing at only 49 items per $1. So that's why the per $8 can be tricky, because you did plug 8 in, but the 8's already accounted for over here. So that's why it should be C and not D. And since the derivative was negative, that's why it's decreasing and not increasing. Okay, now we hit section 4.1 where we first learned the power rule. So now this should be very easy. Derivative of x cubed is 3x squared. And then when you have addition and subtraction, they sometimes call this the sum and difference rule also, but I just think of the whole thing as a power rule, term by term. You just go term by term and do the power rule over and over again. So 2 times negative 11 is negative 22, x to the first power. The derivative of 35x is just 35, and the derivative of 7 is nothing. So there is the power rule term by term or with addition and subtraction. And then we got fractional exponents, we had negative exponents, we had radicals, all different kinds of things. So this is nice because even though there's fractions here, and even though they're negative, I can just use the power rule instantly. So it's literally negative 15 times negative 4/5. And you can just type 15 times 4 divided by 5 to figure out the value of it. And a negative times a negative is positive. So it's positive 12x. The x doesn't change at first. And now you have to decrease the exponent by 1. Negative 4/5 minus 1 is negative 4/5 minus 5/5, which is negative 9/5. Now I go to the next term. 16 times negative 1/4. Well, it's definitely negative something. Positive times negative is negative. So I can just do 16 times 1/4. 16 times 1 divided by 4. Or multiplying by 1/4 is the same thing as dividing by 4. So 16 divided by 4 is 4. So 4x. And then I need to decrease the exponent by 1. Negative 1/4. Minus 1 is negative 1/4 minus 4/4. You just change the 1 to be whatever this denominator is over itself. Negative 5/4. And the original problem had negative exponents, so why can't the answer have negative exponents? You don't have to do that, but it's more work to not do that, so I would just leave it that way. And on each of these power rules, in essence, you were also doing the derivative of the base, but the derivative of x is just 1. So the chain rule is happening there, just it's always x in these early parts of the chapter, so it seems like it's not happening. Find the slope and the equation of the tangent line. So slopes of tangent lines are derivatives. Find the slope of a secant line. That would be average rate of change, but this is slope and equation of a tangent line. So I just have to find the derivative first and plug the numbers in. So y equals x to the 4th minus 25x squared the derivative, this is just a power rule, 4x to the 3rd minus 50 x to the 1st. Find the slope and the equation of the tangent line at the given value of x. X is 2. Oh, I missed this 144, but luckily it won't matter for the derivative because the derivative of a constant is 0. So if I did f prime of 2, this is the derivative at x equals 2, and that would be the slope of the tangent line at that one given spot only. So 4 times 2 cubed minus 50 times 2. 2 cubed is 8. 8 times 4 is 32. 50 times 2 is 100. So the slope of the tangent line at exactly x equals 2 is negative 68. That should be the part 1 answer. Slope of the tangent line at that one spot only is negative 68. If you go to another spot, it could be a totally different slope. X to the 4th problems, they're usually W shapes. So the graph's going to look something like this. In fact, we're going to be doing this in the next chapter. So it's some kind of W shape like this. And if you're at x equals 2 and there's a negative 68 slope, that could be like somewhere here. So there could be a steep negative slope of negative 68. But if I move right here, the slope of that tangent line could be 0. Or this point right here, the slope's positive actually. Then I get another spot that's 0 and another tangent line that's negative. So at every spot you go to on a curvy graph, you get different tangent slopes all the time. So f prime of 2 is negative 68. And therefore the equation of the tangent line is automatically y equals negative 68x plus whatever the y-intercept is. Once you get the slope of the tangent line, negative 68, that's the m in y equals mx plus b. The only tricky thing is I don't know b, so, and you're working with just the regular equation, so then you use x is 2, and you got to temporarily plug 2 into this original equation, not into the derivative function. Plug 2 into the original equation, and that'll get you the y value when x is 2, so that you can solve for b. And this one's big and messy enough that I might do it in here. Parenthesis 2, parenthesis, raised to the 4th power, minus 25, parenthesis 2, parenthesis squared, plus 144. So when x is 2, y is 60. So put 2 right here for x and put 60 right here for y, and then you can solve for b. Y is positive 60. The slope was negative 68, and x is 2. 68 times 2 is 120 plus 16, 136. Yeah. 60 equals negative 136 plus b. Add 136. So that's 196. So all that's saying is this slope here of negative 68, it's a very steep negative when x is 2. A y-intercept is when x is 0. So back up to the y-axis. And if you kept going this way, you would cross the y-axis off screen up here. You'd be crossing at positive 196 is all that's saying. So that now I know the b is 196. I already knew the slope was negative 68 from doing the derivative f prime of 2. Okay, we've got a position function. Anytime you see s of t, velocity, see that's the physics application. Velocity is derivative. You just have to know v of t velocity. That's the derivative of position. So 16 times 2, that's 32 power rule, 32t to the 1st power. Go to the next term, minus 13t has a derivative of negative 13 because that's linear. And the derivative of 7 is nothing. So now I have a velocity function. This, see, it even says here that velocity equals s prime of t, the derivative of position. So then at any given time, like when time is 0, when time is 3, when time is 6, I can find how fast this object's moving. Maybe they drop something off a cliff. Maybe they shot a rocket into the air. So at time of 0, they may have dropped the object already. They might not start the clock until it's already moving. So with v of 0, the object has a negative 13 velocity. So that just means it's moving downward. And then when t is 3, 32 times 3 minus 13. Now the object's moving upward 83 units per whatever. And then 6, put 6 in right here. 32 times 6 minus 13 is 179. Because the original function is quadratic, U-shaped, and apparently this vertex spot is somewhere between 0 and 3, because the velocity at 0 was negative 13, and that's a derivative, so that's a slope of a tangent line. So that would be something like this. There's a negative 13 slope when time is 0. But when time was positive 3, it already had a slope of positive 83 by that point. So the object was moving down, now it's moving up real fast. And then 179, it's even steeper there at x equals 6, and now you're way up here somewhere. And there's a slope that's starting to get close to vertical, 179. So as you move from this side of the curve, your slopes are all negative, but they're getting less and less negative. There's the vertex of the parabola itself where the slope of the tangent line would be 0. That's the one time it's 0. And every point after that, it's positive. We're going to do a lot more of this in the next chapter, actually, which is why I'm pointing that out right now. Here, you don't need to know that just to fill these answers in, but okay, here, now we're up to section 4.2, because now they want me to do the product rule. I have two functions of x multiplied together. That's when it applies. Nothing in the first 10 problems had that. So the original function, oh no, we're on number 12, sorry. Lost track of where number 11 was. Was this 11? Yeah, I was off by one number somewhere. There must have been one that we did where I didn't need to show any work. So, oh yeah, remember that real easy one is how I got off by one number. This is number 12. Okay, 2x squared plus 5. That's the first function of x. This is my first function. Times, and it is times, it's not plus. It's not divided by, it's times 5x minus 2. If this was minus right here or plus, then it would just be a long string of terms, and I could use the power rule all the way across. But I have two functions of x that are multiplied together, not added or subtracted or divided. So dy over dx, derivative of y with respect to x, or you could just call it y prime. I got to go through my product rule. I was about to say, I keep getting power and product. I know which one's which, but I'm saying them wrong. So the product rule is first, as it is, times the derivative of the second. The second function is a linear function, so its derivative is just the 5 in front, so that makes that easy. And then it's got plus. It's the quotient rule that's got minus, but the product rule has plus. Second, you just write it as it is, times the derivative of the first. And the derivative of this 5 is nothing, but this would be the power rule. 2 times 2 is 4, and then decrease the exponent by 1. So 4x to the first power. I could distribute this here and just put the like terms together. So 10x squared plus 25 plus 20x squared minus 8x. So the like terms are the x squareds. 10x squared plus 20x squared is 30x squared. Then I would put the minus 8x next, and then the plus 25. And this way, if this is f prime of x, another way to write it, then I've got the derivative in general, which is all this problem wants, but then I could do f prime of 1, f prime of negative 3, f prime of 0. I could plug in any x's I want to plug in. 30x squared minus 8x plus 25. That was a good review of the product rule. Now it's time for the quotient rule, number 13. So I got two linear functions at least, 9x minus 8 in the numerator. 9x minus 8 divided by another function of x, 5x plus 6. So y prime, or dy over dx. Now we do the second function as is. In the product rule, you start with the first. The quotient rule, you start with the second. A good way to remember that is you learn the product rule first and you learn the quotient rule second. Second times derivative of the first, which is linear, so that derivative is just 9. Minus instead of plus. Now you do the first as is, 9x minus 8. Times the derivative of the second, another linear term, so that would just be 5 for its derivative. And then the other difference is you also do the second function squared in the denominator. Distribute this and get 45x plus 54. And then I would do this. Put this as negative 5. And take that with you while you're distributing. Otherwise, you can mess up the end of that. This is negative 45x, which conveniently cancels with this positive 45x. But here's the tricky part. This is positive 40 right there. Over the second squared. And now I just have this 54 and this 40. And they're like terms, so they can add together to make 94. So final answer is 94 over the 5x plus 6 squared. Most quotient rules, you just have that denominator squared all the way down to the answer. If the x's hadn't canceled out, then possibly I could factor the top and find a 5x plus 6 in it that might cancel with the bottom, but that's pretty rare to see that. 94 over the original denominator, 5x plus 6 squared, because that's part of the quotient rule formula, is you square the denominator. Okay, so now we're doing a business problem where we have cost to a business. Total cost in hundreds of dollars to produce X units of perfume. It's very similar to the previous problem in the way it looks. Find the average cost function. Now that's not calculus. Average cost. Let me write the cost function down first. The cost function is a fraction, a rational function, 9x minus 1 over 3x plus 8 average cost. This is the thing a business likes. You know, when you do an average in math, say you have 4 test scores, you take your 4 test scores, you add them up and divide by 4. So average cost is written C bar X, and you take your cost function and you divide by X, which kind of represents how many things you have. So if it's just a normal thing, like 9x minus 1, you just divide each term by X. But since it's a fraction, the top of this is a fraction, and then you're dividing by X. It's 9x minus 1 over 3x plus 8 all over X, just from the definition of what average cost is. So that's really X over 1. And then you can do my old when dividing fractions, don't be shy, flip the second and multiply. So the top is 9x minus 1 times 1, which is 9x minus 1. Anything times 1 is itself. And the bottom, you just distribute the x in, 3x squared plus 8x. This would be the average cost function. 9x minus 1. See how they put C bar X? That's the symbol for it. 9x minus 1 over 3x squared plus 8x. Find the average cost function. Part B, find the marginal average cost function. Marginal anything is derivative. So now they want me to do C bar prime of X. In other words, find the derivative of this, which is a quotient rule. C bar is average cost, marginal is derivative. And quotient rule, so I need to do second times derivative of the first, which would just be a 9, minus the first. Derivative of the second is just a term-by-term power rule. 3 times 2 is 6, x to the first, plus 8. All over the second squared. So we probably won't have to mess with the denominator. The numerator isn't so bad. In the front, there's a 27x squared and a 72x. So here, there's 2 terms times 2 terms. You'd have to FOIL this. And at first, you would get 54x squared. But then this minus turns it into minus 54x squared. Then there would be a 72x there. But then the minus turns it into negative 72x. And luckily that cancels with this positive 72x. That doesn't always happen. Then there would have been a negative 6x here. But the negative will turn it into a positive 6x. And then there would have been a negative 8, but the negative turns it into positive 8. Okay, so we got 2 x squared terms, and then there's a 6x and an 8, nothing like those two. So 27x squared minus 54x squared is negative 27x squared plus 6x plus 8 over the second term squared. So if the top factors, which is possible, it's possible the top of this fraction could factor, but I really don't care about that unless one of the 2 factors was this denominator factor. If I could somehow get a 3x squared plus 8x for one of these 2, then this would cancel the square of that. But there's no way it's going to happen here because 8x times something would have to equal 8, and there's an x in it, so it's definitely not going to happen. So even if this factors, then it won't matter because I'm not getting the denominator factor out of it, then you don't have to factor it. So then we would just leave it like this. But in quotient rule answers, there's always that danger that maybe somehow the top could have one of its two factors equal the factor of the bottom. And if that happens, then you have to factor and cancel it. It's rare, very rare to, I've seen that happen a few times, but it usually doesn't. So the marginal average cost function in general is this that I just got, unless I have some algebra mistake in here again. But negative 27x squared I think I had plus 6x plus 8. Or is that in the bottom? Let me see. Yeah, plus 6x plus 8. And then I have my original denominator squared. So the bottom is parenthesis 3x squared plus 8x. And then the whole thing is squared. And we'll find out at the end if anything's wrong there. Okay, so then part C. Find the average cost and the marginal average cost for production levels of 25 units and interpret the results. So 25 units, in other words, plug 25 into both of these functions. Okay, so that can get tricky too with how messy these are, but the top would be 9 times 25 minus 1. The top of the first fraction is 224. Then plug 25 into the bottom. 3 times 25 squared plus 8 times 25. The bottom is 2075. So the plugging 25 into this first fraction gives 224 divided by 2075. And it's a messy decimal. So I got to check if they say round anything, then that means they want decimals, but it does say round to the nearest cent. And unfortunately, we're in hundreds of dollars here. So average cost, plug in 25. You're actually getting $2,500. So the average cost for 25 units is blank per unit. So I think we need to multiply our answer by 100 because of this hundreds of dollars. So that's going to move the decimal over twice. 10.795 or 10.80. So my decimal is 0.10795. So if you multiply that by 100, it's 10.795 or $10.80. And then same thing here. First I got to plug 25 in here and then multiply by 100 because of the hundreds of dollars. So the top would be negative 27 times 25 squared plus 6 times 25 plus 8. The top is a real messy negative 16,717. The bottom would be 3 times 25 squared plus 8 times 25. And once you get that answer, square it. And then I need negative 16717 divided by 4305625. So that's negative 0.0038 and then times by 100. So negative 39 cents. So your marginal average cost is going down by 39 cents. In other words, at any instantaneous moment, your costs are going down, which is good. If you're a business person, you want costs to go down and profits to go up. When 25 units are produced, the average cost is $10.80 per unit. And the average cost is decreasing because the derivative is negative at a rate of about 39 cents per unit. Okay, here comes the chain rule for the first time because I have a function of x to a power, but the base is not just x, there's a bunch of stuff there. So first you kind of pretend that all that stuff is just an x. This is number 15. Yeah. 15's got 4x to the fourth. 4x to the fourth minus 5x squared plus 4. But then the whole thing's to the fourth power. So if this big base right here, all in the parentheses, if that was just literally an x, if you just had x to the fourth, the derivative would be 4x to the third. And then you'd multiply by the derivative of the base, which is just 1 when there's just an x there. But if it's not just an x, then that part makes the ending different. But you do the outside part normally like this. So it's literally 4 times 1 on the outside. 4. Then you rewrite the base. Then you decrease the exponent by 1. That's the power rule right there. Times, now I ran out of room here, we're putting this stuff here, but now we need to do the chain rule times the derivative of the inside stuff, which is just a polynomial, so you do it term by term. So I'll try to squeeze it here, times 16 x to the third, and technically times the derivative of this x, but that's just 1, minus 10 x to the first plus nothing. And then you got this 4, and then we usually put the stuff that has a first power next. And yes, you could do a GCF and pull stuff out of here and combine it with that if you want, or you could distribute this 4 in here, but they'll take the answer either way, so why do it if you don't have to? And then 4x to the fourth minus 5x squared plus 4 to the third power. And you can never distribute into a parenthesis when there's an exponent different than 1. So this part's going to be in the answer no matter what you want to do. You can just leave this as is. You can distribute the 4 in. You can pull out a 2x GCF. Any of those would be fine, but they're just extra work for nothing. So 4. And then my first parenthesis is 16x cubed minus 10x. And then my second parenthesis is this to the third power. (5x squared plus 4 raised to the third power, because that was when I wrote the base down and decreased the exponent by 1. So that's a good example of the chain rule in play right there. Okay, so now what's happening is it's looking like the product rule problem from before, but when I get to each of these individual derivatives, the inside base part is not just x, so therefore there's going to be chain rules on each one of those. So 2x plus 1 to the third power times 5x plus 1 to the negative 5. Y prime, or dy over dx. This is a product rule because I have two functions of x multiplied together. So first function, second function. So first times the derivative of the second, and the derivative of the second is like the previous problem. So I do the outside part first. Negative 5 times 1 is negative 5. Rewrite the base. Decrease the exponent by 1. Negative 5 minus 1 is negative 6. But then the base isn't just x, so the derivative of 5x plus 1 is 5. There's the chain rule getting tacked on. This part is just the derivative of the second. Plus the second times the derivative of the first, and that's a chain rule too. So that's going to be 3 times the base to the second power, and then times the derivative of the inside. So let me put it down here because I ran out of room. 3 times the base, decrease the exponent by 1. The 3 minus 1 would be a 2, times the derivative of the inside, which is just 2. Okay, now everything, all the parenthesis parts have exponents attached to them. So we definitely can't distribute into them. We definitely can't pull any kind of GCF out of them. So there might not be a whole lot of simplifying here. I could do the negative 5 times 5 and get a negative 25 in the very front. And then I'm just going to put the two parenthesis parts after that. 2x plus 1 cubed. And 5x plus 1 to the negative 6. There's no way to do anything with this on its own. Unless you wanted to like FOIL this out a bunch of times. You could put this negative 6 in the bottom, but it's really not needed, so I'll just leave it there. So plus, similar deal here, I can do the 3 times the 2 and get 6 in the front. And then I got my two parenthesis parts again, 5x plus 1. This one's to the negative 5. And then the 2x plus 1 is to the second power. You can't do anything with this alone. You can't do anything with this alone. The one thing you could do is you could say, oh, wait, there's a GCF of 5x plus 1. There's a GCF of 2x plus 1. You could pull those out front and just see what's left, but it's probably not needed. So it's just extra algebra that you could do, but it should take this answer as well since there's no way to simplify this individually. So negative 25. And this is another good thing about this review video is you can watch me do stuff when there's maybe some debate about how should we keep simplifying or not. So you can watch me do it, and then if it counts me wrong, then you'll know, okay, we were supposed to do something like that, and then at least you won't miss it when you're doing your review. So 5x plus 1 to the negative 6 plus 6. And you could put the 2x plus 1 first here too, but I'll just keep it in the order I have. 5x plus 1 to the negative 5. And then the 2x plus 1 is raised to the second power. Yeah, positive 2 right there. So other than pulling a GCF out, which is really just an algebra step anyway, there's no way to simplify this in any way. If you did do that, there would be a 2x plus 1. When you pull out a GCF, for variable parts, you always grab the smaller exponent. The greatest common factor is the one with the smaller exponent. So there would be 2 of those if you did that. And then for your 5x plus 1, negative 6 is smaller than negative 5, so that would be negative 6 here. And then you'd still have the negative 25. And you pulled out 2 of the 3 of these, so there would still be 1 of those there. And then you pulled out all of this, so that's it for that. And then you'd have your plus 6. And then you pulled out negative 6 of these negative 5, so there actually would be 1 more left over. And then you pulled out both of those, so that's done. And this could be an equivalent answer. If you wanted to do that, you could even then distribute here and put like terms together. So that's all possible too. But again, all this is just extra algebra steps that I'm pretty sure don't have to be done. And we'll find out when it grades me. Okay, so we have two things left, sections 4.4 and 4.5. This is derivatives of exponentials and derivatives of logs, which we've done both recently. The last two videos. So if you have an exponential with a base e, negative 5e raised to the negative 4x plus 2, that is exponential where the base is a positive number and the exponent has the x in it. So the derivative of any exponential is itself first, exactly as is. Then you technically multiply by ln of whatever the base is. But ln of e is equal to 1, so then it doesn't matter. And then the chain rule, then you multiply by the derivative of the exponent. And since that is a linear term, a linear function, then you just have the negative 4 for the derivative of it, the slope of the linear. So then this negative 4 could get multiplied to that negative 5, and you could get positive 20 e to the negative 4x plus 2. And that would be it for this one. 20 times the original e to the negative 4x plus 2. And then here we have x to the 10th times e to the x. So this would be a product rule in the middle of also doing an exponential rule. That's the other thing when you get towards the end of the chapter, then they can throw any of the past rules at you at any moment. X to the 10th, that's power. I've got a power function of x times an exponential function of x. This is my first function. This is my second function since they both have x's in them. So the derivative, I'm going to use the product rule first times the derivative of the second. And the derivative of e to the x is literally e to the x. That's one of the rare things whose derivative is literally equal to itself, because technically I should also multiply by ln of e, which is 1, and then I should multiply by the derivative of the exponent, which is 1. So e to the x is its derivative is e to the x, it's itself. Plus the second function times the derivative of the first, which is power rule, 10x to the 9th. So again, you can probably leave it like this, although I'd probably put the 10x to the 9th in front. This should be a good answer. There is a GCF of x to the 9th and e to the x. And if you take 9 of the 10x's away, there'd literally be just one left. And you already took the e to the x away in both of them. This is just an x here. And then you took the x to the 9th away, so there's a 10. So you could do this, but it's just an algebra step of pulling the GCF out. It doesn't really make anything nicer or anything cancel or anything like that. So that's usually when either answer is acceptable. So x to the 10th, e to the x. Plus 10x to the 9th, e to the x. 10x to the 9th, e to the x, yeah. Now we should have a couple of logs to do, okay? So negative 9x, see that's a function of x. And then ln has a function of x, 9x plus 1. This is another product rule. If they would have just given me a negative 9 instead of a negative 9x, then it would just be a log rule only. But negative 9x, that's a function of x. And then anytime you put something right next to it, it means times. I've got two functions of x multiplied together. There's the first function. There's the second function, and they're multiplied together. So once again, first times the derivative of the second. Here comes the log rule. The derivative of a log, first you do 1 over the original stuff. In exponential, you just do the original stuff. In log, you do 1 over the original stuff, since they're inverses of each other. Then there's times 1 over ln of the base, but this base is e, so this will just all equal 1. And then times the chain rule, the derivative of 9x plus 1 is 9. And all of that is still just the derivative of the second. I haven't even halfway finished the product rule yet. First times derivative of the second plus the second times the derivative of the first, and that's the one easy step here. The derivative of 9x, negative 9x is negative 9, since that's linear. So we can do a little bit of cleanup here. This times 9 and this negative 9x, you could make that negative 81x. And you could either put this 9x plus 1, leave it in the bottom, or put it up in the top as to the negative first power if you really wanted to. But nothing here reduces. You can't reduce this x with this x. And you can't reduce this 81 with this 9 because of the plus right there. You'd have to factor something out of this entire term. If you had like 9x plus 9 instead of 9x plus 1, then you could pull a 9 out and have x plus 1 left. Then, because it's 9 times, then you could reduce the 9 with the 81. But that didn't happen because it's 9x plus 1. Plus or minus, I guess. I could just put this minus 9 next. ln of 9x plus 1. So not much simplified after I did the product rule. Negative 81x over the 9x plus 1, which does not simplify in any way, minus 9 ln of 9x plus 1. Negative 81x over 9x plus 1 minus 9 ln of 9x plus 1. And then what happens if the base is not e is the only last condition here, or last type of example. So if my original function is log, not ln, log of 11x, log is log base 10. When they leave it blank, it's a 10 if it's log. ln is actually base e, but log, common log, that is base 10. So first, the derivative of any log, whether it's natural log or not, the derivative of any log is 1 over its stuff in its domain slot. And then you do 1 over ln of its base, which would be 10. And then times the derivative of the inside, which is a chain rule. The derivative of 11x is just 11. So there is no addition or subtraction here. Then 11 can cancel 11. If this was 11x plus 1, then you wouldn't be able to do that. So there's nothing left in the top other than 1s, but then you can't have a blank top of a fraction, so you got to have a 1 there. And the bottom is just this, literally, x times ln of 10. So final answer, 1 over x ln of 10. Okay, so I've answered all 20 questions, and now we're going to hit this submit button up here. And we'll see if I missed anything, and they warn you because you could submit it before you've answered every question if you already have a grade you're happy with. 100%, 20 out of 20. Everything's got a green check. That's good. So clearly, if you get 100 doing this one time, then you don't have to do it again if you don't want to. But even if you do get 100 on it, if you are right before your test, if there's anything you're like a little iffy on, and oh, I got that right, but I don't really feel I did that exactly right, or feel that I might get it right on a test, then you could always do that again on the review. So I could do this review a second time, and I could literally just do one problem. If I felt like, where was that one that had all the GCF stuff in it? This one here. See, I wasn't sure if they were going to take it this way. I thought they would, but so I could do this problem again just for more practice, or I could even pull GCFs out and see if they take that version of it. It's none of that's needed, but I could do that. And then if I submit the quiz a second time, this review a second time, even if I only do one problem, and then my best score is going to be a 5% that time, or if I get a 0 because I missed the one problem that I retry, as soon as you have a grade you're happy with, if that's your highest score, 100 or a 95 or a 90, then you can't lose that score. So that's what's nice, is I can do this a second time, and now I don't have to do all of it if I don't want to do the whole thing all over again, since I got all of them right. But or if you get close to all of them right. So there's a pretty good review of all 7 of these sections here: 3.3, 3.4, 4, 1 through 5. One advantage here is these 3 3s and 3 4s took a lot longer when we learned them. Now with all these derivative rules, you can help speed the process up here, because this took me just about an hour and a half to do all that review, even with some shortcuts along the way. So we're going to be doing more with derivatives in this section, in this chapter, chapter 5. And then there's some other stuff in chapter 6 we cover too. But these first 4 sections of chapter 5, they're all about using what derivatives tell us about a function. So if you have an original function, the derivative tells you stuff about it. And that's what you're going to learn in these 4 sections. And then chapter 6 is just a little bit different. Okay, so we're all done with review for test 2. So good luck on the test, whether you take it on Thursday or Friday.